Let's now kind of describe these forces a little bit. Let's draw them out here and make a bit more sense of this. Okay. And feel free to put questions in the chat as usual or stop me as we continue to go here. So let's describe the Starling's forces and actually illustrate them here. So Starling's forces. And let's first draw our capillary. So this is our capillary here, the length of our capillary. And then we've got a tissue level or tissue that is in close proximity to this capillary. So here is a tissue. Here's our capillary. And then here is our interstitial fluid space. This is what we mean by that fluid compartment that's surrounding the tissue. So this is the interstitial fluid space or fluid compartment. Okay. And then let's also point out that this is our arterial end. And this is our venous or venule end. Oops. Okay. Let's make a little key here in the upper right corner that describes these variables here. So large P is going to be representing our hydrostatic pressure. In other words, our push force, okay? And then in blue, we'll put the pi, which is the symbol that represents our oncotic or osmotic pressure, which is our pull force. Okay, so let's kind of fill these pressures in. So let's start with the hydrostatic pressures first. Remember, we have hydrostatic pressure in both our fluid compartments. So in our capillary, in brackets here, I'm going to put plasma so that we understand that plasma is the fluid compartment inside our capillaries. Okay, and so the first force is going to be our capillary hydrostatic pressure, and that's represented with CAP and then the large P. And that is going to be pushing fluid from the capillary out into the interstitial fluid space. Okay. Remember, this is a push force, and because it is in the capillary, it's going to be pushing away from where it's located, so out into the interstitial fluid or the interstitial space. The other, or the second hydrostatic pressure is our interstitial fluid hydrostatic pressure. That is represented by IF here, and then that large P once again. And so this is basically the force that is pushing fluid from the interstitial space back into the capillary. And so this is likewise going to be a push force moving fluid in the opposite direction. So capillary hydrostatic pressure pushing fluid from the capillary out into the interstitial fluid space. And then interstitial fluid hydrostatic pressure pushing fluid from the capillary back, from the interstitial fluid back into the capillary. Okay. Let's look at our osmotic or our pull forces as well. The first pull force is going to be the capillary oncotic pressure. And remember, we talked about these proteins that are staying back in the capillary here. The main one being albumin. I'm going to go ahead and write albumin here. This is our main oncotic protein. This is why albumin is so important in the blood. It helps to maintain this pressure, this capillary oncotic pressure. Someone's asking just to clarify if there's a structure beneath the capillary. No, there isn't, right? So just the capillary below and then the tissue above. Okay. So albumin present in our capillaries exerts this capillary oncotic pressure, which again represented here by the symbol pi and then CAP representing the capillary. And because this is a pull force and the presence of these proteins that cannot cross this membrane, they are going to exert a pull force from the interstitial fluid space back into the capillary. Alternatively, we also have an interstitial fluid oncotic pressure as well. So that is going to be the fluid that should be based on the presence of proteins in this space. And I'm saying should be here because really there should never be proteins, or there never are proteins in the interstitial fluid space. And so while we still want to acknowledge this value, it usually is 0, okay? But the force that this would be exerting is a pull force from the capillary into the interstitial fluid space, okay? Being a pull force towards the interstitial fluid, okay? And I hope that is clear so far. Let me just write here in, oh, I do have interstitial fluid. So this is the interstitial fluid. I'm gonna just make it more clear here. So we understand that there's a fluid compartment here. And so these are the two areas that are exerting the two different forces, right? So each area is exerting both forces. And so we really want to net these forces out in order to determine where does fluid really end up going, right? We're not going to ignore any of these forces because they're all acting on the capillary wall. And so what we really want to do is start looking at the forces individually, plugging in the values for these forces individually, and then netting those forces out and seeing where the fluid movement actually is happening, where the overall net force is in favor of. Is it in favor of filtration or is it in favor of absorption? And remember, when we talk about filtration, that is a net movement of fluid from capillary out into the interstitial fluid, whereas absorption is the net movement of fluid from the interstitial fluid space here back into the capillary. So let's further describe it here at the bottom. So filtration is a net movement of fluid from the capillary, where the plasma is essentially, to the interstitial fluid space. Okay. Whereas absorption, on the other end, is the opposite net movement. So that's going to be net movement of fluid from the interstitial fluid compartment, and I'm going to just put ISF here, interstitial fluid compartment, to the capillary. Okay. And so as we start netting these forces out, combining these forces and netting them out, we're looking for this general theme. Is the overall movement favoring filtration, or is the overall movement favoring absorption? Okay. All right. Okay. So let us start plugging in some values here for each of these different forces. Let's start with the hydrostatic pressures or the hydrostatic forces. So essentially at the arterial end and the venous or venule end of our capillary, we actually have two different hydrostatic pressures. Remember, the hydrostatic pressure is due to the pressure exerted by the fluid in the capillary. And we know that as we move from the arteries into the venules and veins, pressure drops off. And so when we go from the arterial end of our capillary to the venule end of our capillary, pressure too drops off. At the arterial end, the hydrostatic pressure is about 38 millimeters of mercury. And by the time we get over to the venous or venule end of that capillary bed, the hydrostatic pressure has dropped off to 60 millimeters of mercury. Okay. Now, this is a force that we said favors filtration. In other words, because it's a pushing force, it's pushing fluid from the capillary out into the interstitial fluid space. We see that this force overall favors filtration. If you look at the interstitial fluid hydrostatic pressure, so this is now the hydrostatic pressure in the interstitial fluid space, it's usually very low, usually around 1 millimeter of mercury. And so we say that this is a pushing force going from the interstitial space back into the capillary. And so that overall movement, as you would imagine, favors absorption, okay? Moving from the interstitial space back into the capillary, that will favor absorption. And so if we calculate the difference here at the arterial end, if we subtract the hydrostatic pressure, or excuse me, the oncotic pressure from the hydrostatic pressure, we end up with a difference of 37 millimeters of mercury. So that's our overall hydrostatic, our overall force rather that's moving across the capillary. And so when we look at the venous or venule end, we subtract that same oncotic, not oncotic, I keep saying oncotic, please excuse me guys. This is the interstitial fluid hydrostatic pressure. So let's say this one more time. At the arterial end, we subtract the interstitial fluid hydrostatic pressure from the capillary hydrostatic pressure, and we end up with a difference of 37 millimeters of mercury. So that is the difference between the hydrostatic pressures at the arterial end, and on the venous or venule end, once again, we subtract that interstitial fluid hydrostatic pressure from the capillary hydrostatic pressure, and so we get an overall hydrostatic pressure of 15 millimeters of mercury. Okay, please excuse me, there is no osmotic pressure taken into account here just yet. And so the overall hydrostatic pressure is going to favor filtration. We know this because it's going to favor that movement of fluid going from the capillary out into the interstitial fluid space, okay? In terms of the osmotic pressures, we can plug in some of these values here as well. So the capillary oncotic osmotic pressure is about 25 millimeters of mercury. Again, this is a pull force. This favors absorption. It's going to be moving fluid from the capillary over into the interstitial fluid. And the interstitial fluid oncotic pressure is going to be moving fluid in the opposite direction. It's going to favor filtration. This is where we say this is very low. It's usually negligible, 0 to sometimes 1 millimeter of mercury. And this is because there shouldn't be any proteins in the interstitial fluid to exert this pull force into that space. Okay, and so when we net out this pressure, we get 25 minus 0, which gives us 25 millimeters of mercury, favoring absorption. In other words, moving fluid from the interstitial fluid back into the capillary.